So yeah, thank you for having me here. Let me start with my research interest. So my interest lies in using gravitational wave multi-messenger observations to study various questions in astrophysics. And I noticed that you already have some gravitational talk recently, so I'm going to skip some of the introductions and maybe go directly to the source. So these two types of stars, they compose of our major source of interest for LIGO and Virgo. I'm going to use the orange ball to represent the neutron star throughout the talk, and a blue ball for stellar mass black hole. The binary merger of these two types of stars, they compose of all the LIGO Virgo detections so far. We are detected, for example, more than 80 binary black hole mergers spreading across a wide range of masses. We also have detected lighter objects like a merger between two neutron stars. And so far we have two detections like this. One of them even comes with electromagnetic counterpart, including kilonova and short gamma ray burst emissions. And we're gonna come back to this later. These electromagnetic emissions, they can bring us complementary information about the system so that we can later combine this information with what we learned from gravitational wave to jointly study different questions we want to study. And you're gonna hear some examples throughout the talk. Astronomers also did try to look for electromagnetic counterpart for binary black hole mergers, but so far there is no electromagnetic signal that is widely accepted to be associated with a binary black hole merger yet. We have also detected the merger between a black hole and a neutron star. And for this type of neutron star black hole mergers, we have roughly two detections like this. There's an approximate sign there because we're not 100% sure about one of them. And the electromagnetic observing conditions for these two events weren't very good. So we were also not so sure whether they came with electromagnetic counterparts or not. So we do need more observation to really confirm this. All right, so with these three types of sources, some of them even come with electromagnetic counterparts. There are various questions we can try to study. And in this talk, in the first part, I'm going to talk about how we're going to use these gravitational wave observations to try to answer some questions in cosmology. And in the second part, we'll move on to some applications in the neutron star nuclear physics. Okay, so let's start with cosmology. There is this well-known tensions about the Hubble constant measurement between the early universe measurement from CMB and the local universe measurement. And currently the tension between the two type of measurement is as large as pi sigma. And is this systematic? Or do we really need a new theories to interpret the universe? That is a big open question in cosmology now. And that is also where gravitational observation can possibly play a role, because we can provide a completely independent measurement of the cosmological parameters via this so-called standard siren method. So how does this standard siren method work is the following. Suppose we have a gravitational wave signal that is captured by the LIGO Virgo detector, and we also happen to capture its electromagnetic counterpart. Most of the traditional telescope, they are able to localize the gravitational wave source very well, much better than what LIGO Virgo can do. So this good localization will allow us to associate the gravitational wave source to its host galaxies. Then by measuring the redshift of the host galaxies, we can determine the redshift of the gravitational wave source. On the other hand, the gravitational wave side, the signal directly carries the information about the luminosity distance to the gravitational wave source. So By combining both of these information into, for example, this standard expression in cosmology in which we relate the redshift to the distance via a set of cosmological parameters, including h0, omega matter, omega lambda, etc. Then with these information, both of them, then we can constrain these cosmological parameters. And especially for LIGO Virgo sources, since they are relatively local, so we constrain the leading order term, the h0, Hubble constant the best. And that's what's being done, for example, for the first binary neutron star merger detection, GW170817. What you see here with the blue solid curve, that is the posterior of the Hubble constant measurement coming from the observation of the binary neutron star merger and its kilonova counterpart emission. And as you can see, the uncertainty here is actually very big. It's much bigger than the tension between the CMB and the supernova measurement here. But we do expect this kind of gravitational wave and electromagnetic wave joint detections to happen more often in the future. So here's a projection of the number of joint detections as a function of time. So going to the right-hand side is going to the future. And the vague green band here is trying to capture the major uncertainty of this estimate, which came from how often did this binary merge in the past, the astrophysical rate of binary merger, binary neutron star mergers here. And let's say now you combine this event, then this is the precision of Hubble constant you would expect to achieve with these detections. Especially after the LIGO Virgo third observing run, the so-called O3, it seems that the neutron star merger, binary neutron star merger rate tend to lie at the more pessimistic end. But even so, we still expect percent level of precision in the Hubble constant measurement only within a few years. And that is the precision that could be interesting, that can possibly say something about these tensions in the Hubble constant.
How many sources do you need to achieve this precision level?
So roughly for say 2%, that is 50 joint detection you need, and that will take a few years.
So you get the redshift out of the optical counterpart. That's the only thing you get out of the optical counterpart, or is there more?
In principle, that is the only thing you need. We will talk a little bit more later about some other information you can possibly use, and that will help your measurement. Okay, so this is.
And I assume the dominant source of uncertainty is in the luminosity distance measurement.
Yeah, we'll go there soon. All right, so this is the approach using electromagnetic counterpart, but you might also heard of a very similar approach that is not using electromagnetic counterpart. Instead, they're using galaxy catalog. So by statistically combining all the potential host galaxies within the galaxy catalog, we can estimate the redshift of the gravitational wave sources. There's a nickname for that, it's called dark siren, because there's no light really directly involved. So, however, you can see from this comparison here we already assume the galaxy catalog to be complete. So that is already a difficulties. Another thing is that there are actually various systematic that's associated with this dark siren approach. But even if we ignore all that, this is the kind of precision you can possibly achieve with dark siren. And as you can see, it is very unlikely for the dark siren to give you a H0 measurement that's anywhere close to the bright siren, the one using electromagnetic counterpart. And that's why for the last few years, my work actually been focusing on improving the bright siren approach. If you really want to get rid of the electromagnetic counterpart, likely you will have to wait a bit longer.
Sorry, why is the slope? The slope is changing because of the upgrades. Like there's a particular kink in the detect, like in the
slope. Which slope?
In the top curve, like there's a kink. No, in the top panel.
Green.
Yeah.
Oh, it just depends on which network, which sensitivity you're assuming. So like this might be for a 1 year, and this might be 1 year, but with higher duty cycle and higher sensitivity. So I didn't do a continuous simulation, but only 5 points or something. That's why there's a kink. Okay. So if we really want to get rid of electromagnetic content part, that is something you might need to wait a bit longer when the next generation of gravitational wave detectors coming online. By then there are some possibility for us to localize the gravitational wave source within a very small volume. And that's great. Localization will allow us to directly associate the gravitational wave source to its host galaxy. That's something I've been looking into with MIT grad student Jeffrey Moore. And actually, Jeffrey just sent me a preliminary result I'm going to show you here, which is, so this is a simulation for 30-30 solar mass binary black hole mergers. And we found out that for the binary black hole merger within 1 gigaparsec, 70% of them will be able to localize them within about 100 cubic megaparsec. And we pick 100 as a boundary or a division here because that is roughly, you roughly expect 1 Milky Way-like galaxies within 100 cubic megaparsec. So below this, if you can localize the source within or below this number, then possibly you could directly associate the gravitational wave source to its host galaxies. But actually, when we are working on this, since we're talking about next generation, that's beyond 2030. So by then, possibly H0 might not be the focus or might not be the question we are trying to answer. So this direct association, what I'm thinking is that they might help us to solve the formation history for the binary black hole mergers. Because currently our approach to understand how these binary black holes form was based on the observation of their mass, their spin, their centrifugal rate, and we have to gather a population of them to really try to reconstruct the history. But there is no talking about a direct association to their host galaxy. But if we can identify their host galaxy and figure out what is the particular type of host galaxy that's hosting those binary merger, then that will give us some extra, more straightforward, more direct association with their formation history. So that is somewhere, that's the direction we are heading for now. Go ahead.
So about this direct association, does it still rely on a complete galaxy catalog?
So for this case, let's say you are able to localize it within a very small volume. You don't really need the galaxy catalog prepared before that. You actually can point your telescope after you know which direction you want to look at so that you save a lot of resources.
And it is possible that like this binary neutron star merger like preferentially located at like lower mass galaxy, and therefore that can make the galaxy catalog part more difficult.
Galaxy catalog.
So I mean that, for example, if they're preferentially in some like dwarf galaxy, for example.
Yeah, that could give us some difficulties. Like especially if you want to, if what you are trying to do is try to really identify which exact galaxy it is, then that could be difficult. For cosmology measurement, that might not be that big problem because as long as you can identify which local group, which group it belongs in, then you can determine roughly the rest of there. And so that approach is possibly easier. Yes.
Yeah, I was wondering, so for example, depending on the complication of the source, you might, if there's higher modes, for example, you might be able to determine the inclination.
That's what we are heading for.
I think it's very important for the distance. So I was wondering what was assumed here for the type of sources and whether maybe there are some better ones or for doing this calculation.
So there are different settings for different simulations. For this particular one, Jeffrey just showed this one is very simple. This is only 30-30 solar mass binary black hole merger. We did not consider higher order mode. So if you consider that, then that will give us something, maybe a factor of few. I wouldn't say more than factor of 2, because if you want to get some, I've seen cases like a factor of 5 or something improvement, but that is some special ideal situation. So at most factor few better in distance, you can get that improvement from higher order mode observations. But here we didn't assume that. Okay. All right. So back to the standard siren. Basically, if we're only talking about the next few years, then the gravitational cosmology will still heavily rely on the identification of the electromagnetic counterpart, which for itself, there are difficulties. There are many difficulties actually, but I'm just going to summarize it into, say, 2 points. First one, we've already talked about. LIGO Virgo, we are not able to localize the source very well on the sky. And a lot of these electromagnetic counterpart emission, they don't last forever. They fade away over time. So if the astronomers are not able to point their telescope to the right direction at the right time, then you can miss this electromagnetic counterpart. So I've been trying to work on these problems from various directions. For example, with LIGO Virgo folks, we try to speed up our localization of the gravitational wave source. So it reduced from days to weeks to basically within a second. So within a second, we actually can produce a sky localization map after we identify the source in our detectors.
Addition, your main worry is that you might only see the peak emission, or because I mean the afterglow can last for very long, but the peak is like a day. Oh
yes, but for identification of the source, you mostly relies on those shorter duration electromagnetic counterpart. You first need that, then you can try to follow the afterglow. Yeah. Okay, so that's one approach. Another thing another idea I just had a few years ago is I call it gravitational wave weather forecast, which allows us to forecast from which direction on the sky the gravitational wave source is most likely come at any given time. And that is using some interesting characteristic about our interferometers. We can talk about it if you are interested after the talk. And also I've been working with some astronomer in Degeneracy survey. Our team identified the kilonova emission in 2017. But there are still various different directions we can try to improve the electromagnetic counterpart observation. And if that is something you're interested, we can talk after the talk. But let's come back to the standard siren method. So I've been wondering, like we are talking about percent level precision of H0 for a few years, but I've been wondering if there's different approach we can try to do better than that. And to look into this question, you first need to ask then what contribute most to your H0 measurement uncertainty. Turns out it comes from the distance uncertainty that's from gravitational wave side. And then why can't we measure distance that well? The dominant factor turns out to be this distant inclination degeneracy. So what is this degeneracy? Suppose you have a binary neutron star, they are emitting gravitational wave. The gravitational wave emission is strongest along the rotational axis of this binary. So now you can imagine if this rotational axis is parallel to your line of sight, like a face-on binary on the left-hand side. And then you compare the gravitational signal coming from a face-on binary to an edge-on binary. So the rotational axis is perpendicular to your line of sight. If everything else is same, then you would expect the gravitational signal coming from a face-on binary to be stronger than an edge-on binary. However, we can push this face-on binary further away, then you can easily have a signal that looks identical to an edge-on binary that's close by. And that's why if you don't know the inclination angle of the binary, then you can suffer from this distant inclination degeneracy. And there are several possibilities to break this degeneracy. One possibility is to turn our attention into this new type of source, neutron star Glacos merger. So what's great about this type of system is that, first of all, there's a neutron star in the system, and this system can be tidally disrupted by the companion black hole thrown out material. This material can then power up electromagnetic emissions. So this type of system, they can possibly be bright in the electromagnetic spectrum. Another great thing about this is that this kind of system, they can have precession. So since in this type of system, they have a black hole. This black hole, they can have spin. If the spinning axis of the black hole, the blue arrow there, if they misalign from the total angular momentum of the system, the yellow arrow there, then the system, they can go through a precession. And that precession can allow us to observe some higher order mode in gravitational wave signal. And these higher order mode are different from the typical dominant mode we observe. And they have this higher order mode, they also have a different dependencies on the binary inclination angle. So if we can capture this higher order mode, then we can capture extra information about the binary inclination angle, then it helps us to break the degeneracy. So here is how well we can constrain the distance for system with and without precession. As you can see, for system, binary system with precession, you can expect at least a factor of few improvement in your distance measurement. So basically each neutron star black hole merger system like this, you can just view it as a golden event. Each of them will give you very good distance measurement. And that also means that each of them can give you very good H0 measurement, because distance, as we mentioned, distance uncertainty, as we mentioned, is what dominates H0 uncertainty. So we found out that as long as the universe can produce one neutron star black holes merger, this kind of golden event like this, for every 10 binary neutron star mergers, then these neutron star black holes merger altogether, they can give us actually more precise Hubble constant measurement than all the binary neutron star merger combined. So that is one possibility. Another possibility, as we also being asked, this is about using extra information from electromagnetic observation.
Sorry, can I ask
Yes.
on that point? So you mentioned neutron star black hole, but it's binary neutron star. And the spins of neutron stars are generally expected to be small. So the precession effects would be not.
That is why, yes, right. That is why we don't expect strong precession for binary neutron star merger.
But I'm a bit confused, like all the binary black holes with extreme mass ratios also.
They can also have precession, that's right, but they don't emit light. That is another downside.
No, but here the previous slide I thought was breaking this distance inclination degeneracy. We could break it better that way.
Better, yeah, they can do better if they have strong precession.
So about the neutron star black hole case, and if it has a tertiary companion, does that contribute to like some additional precession term?
If they have a
tertiary companion, so if they are in a three-body system, yeah, will that affect anything here? For example, contribute some additional precession signal.
I think the signal will be quite different if you are a three-body system, and by then, at the time when the two of them merge, the third one possibly has been kicked out or something, or relatively irrelevant. Like by then, when the two of them merge. Okay. All right. So another possibility to break this distance inclination degeneracy, which is by using extra information from electromagnetic observation. Here's a nice animation that's made by NASA for the electromagnetic emission from a binary neutron star merger. We have the elongated jet, that is a short gamma ray burst. We also have the kilonova emission, that is more isotropic, but still there are theoretical prediction and a little bit of observations support saying that the kilonova emission, they can possibly have some sort of structure as well. So if we try to interpret those electromagnetic observation, then we can possibly put some constraint on the inclination angle. We can call it a viewing angle of the binary. If we do so, then we will need a factor of 5 to 10 fewer events to achieve the same kind of Hubble constant precision. And this is an approach that's already being applied on the GW17 or 17 observation. But one question you would immediately raise when you hear this approach is that, well, these electromagnetic emission, they are so complicated. We don't understand them that well yet. So what if your inferred binary viewing angle is biased? If there's a bias, then that's gonna propagate to your distance estimate and then to your H0 measurement. It's gonna bias your H0 measurement, which is the last things you want, especially what we are trying to answer from the gravitational wave cosmology side is trying to resolve this tension, and you really want to make sure your systematics is under control. So I tried to look into this a bit further. Let's say we start with some simulated event, starting at some viewing angles. But now let's say we either underestimate or overestimate this viewing angle. We can repeat these simulations in some fiducial cosmology. I picked the Planck H0 value as my fiducial cosmology. Then depending on either you underestimate or you overestimate this binary viewing angles, this blue band is what you would recover after combining certain number of events. And as you can see, even with a 10 degrees bias in your binary viewing angle, it can push your H0 value all the way from the Planck value to the Schiu's value, the supernova value. So I would say if you really want to use this extra information from the electromagnetic wave side to infer the viewing angle, you really need to make sure your bias, your systematic for this viewing angle estimate is 10 degrees. So I would say even much less than that to be safe. Yes.
Which angle does the electronic signal measure? Is it the spin axis of the black hole, or is it the orbital plane? So is that clear which direction the jets launched in a binary neutron star merger? In a neutron star black hole merger?
Which axis do they measure?
In other words, one might imagine that the jet comes out the spin axis of the black hole.
Yeah, so that is actually the assumption.
The actual orbital plane, but on the other hand, maybe you think the disk is in the orbital plane and it comes out that. It's not clear to me which angle it actually comes out from. Do we know from theory which?
So what we measure from the electromagnetic wave side is this angle relative to the rotational axis of the binary. But that is under the assumption that actually let's say if you actually capture this information from short gamma ray burst, for example, then you have to assume the short gamma ray burst, the jet direction is actually aligned with your binary rotational axis. So that is.
That's I guess what I'm asking is, do we know that's true? That
we don't know. So that is
if you merge like irrotational components, right? I mean, you end up with most of the orbital angular momentum and spin, and then you get like a spinning black hole of 0.7 just being aligned with the former orbital angular momentum axis. And so
you mean the orbital angular momentum dominates the black hole?
Yes, exactly.
I see. So
it's a good assumption to assume that then if the jet launches along the spin axis of the black hole, that roughly coincides.
Can you violate that
yes,
significantly by anything?
For neutron stars, it's very hard. You can violate this for like black holes if you do some either counter spinning ones, then you can get. Because neutron stars only have like maximal spins of like 0.5 and the orbital one gives you like 0.8. So really killing that off is almost impossible if you want these type of events. And then, I mean, from the gamma ray burst, you get like this 30-degree off-axis viewing angle, right, that you were mentioning.
It must depend on the mass ratio between the black hole and the neutron star. In other words, if you have a higher mass black hole, you might think that
but there, if the black hole gets too massive, then you don't get any remnant matter, then it eats the neutron star hole. So I guess for neutron star black hole, you would need something with like black hole mass not larger than 5 or something.
Yeah.
Okay, so then it's sort of a guaranteed to be a low mass black hole, as it were.
If they exist.
And then one might imagine. Okay.
All right. So. Okay, so so this is difficult basically. We don't understand them that well yet. So some people might say, well, then forget about it. Just don't use this extra information and problem solved. But then I realized the problem is not solved this way actually, because as long as your your electromagnetic emissions have some sort of dependency on the binary viewing angle, then that means the sample available for you with joint detection, with gravitational wave and electromagnetic wave joint detection, they go through a selection over the binary viewing angle. Then that also means that when you try to infer the H0 from these samples, you have to correct for this selection effect. Otherwise, you can get a bias. So let's look a bit further into this. Let's say, okay, we start with this simulated event again, but let's say now we can only observe this electromagnetic emission within certain cone. You can define a maximum electromagnetic wave observable viewing angle based on that. You can imagine the smaller this angle is, that means the cone is also smaller, and that's a stronger selection effect. Again, with this fiducial cosmology, we found out that if you understand this selection very well, then no problem. You can reconstruct the H0 without bias. However, if you don't know about this selection, this blue band is what you can end up with. Again, you can start with the Planck value and you end up with the Schu's value of H0. So this comparison is really telling us, well, it's highlighting the importance for us to really understand the geometry of the electromagnetic emissions so that we can properly correct for this selection effect. And we can even compare this kind of systematics, this is a new one, and the fight to other known sources of systematic for the standard siren method here, and there's some of them, and especially the third one. This one related to the calibration uncertainty of our instrument, which comes from the fact that we are not able to monitor the position of our mirror inside the interferometers that well all the time. So that is a calibration uncertainty. This one was long thought to be the dominated source of systematic for the standard siren method. However, with the recent work led by Eva Huang, another MIT grad student, we worked with the LIGO calibration team, and we found out that these kind of miscalibration, they actually don't happen that frequent. So they don't happen frequently enough to really affect the accuracy of the H0 measurement. Then the next one down the list turns out to be this new type of systematic associated with the viewing angle. So that is something we'll need to work toward trying to mitigate that. Currently, I'm thinking maybe we can try to use, well, of course, new observation of kilonova, and also possibly with the numerical simulation of this kilonova emission, combining of them, we might be able to model all this kind of systematic, but work to be done.
When you did this estimate, did you assume that you had found the counterpart through the GRB or through the kilonova? They have very different, assume, the emission profile. I mean, the kilonova is much more round or whatever, spherical. Is that true? What was assumed for the really bad stuff?
So you can assume that you observe some sort of electromagnetic counterpart. It doesn't need to be any type, but some you identify it. You have a very good redshift measurement, a precise redshift measurement, and then you need to assume what is the probability for you to capture the electromagnetic emission as a function of the viewing angle. So that is the assumption, and then we try different possibility from the very narrow, very highly selective one to a less selective one. Or you can even assume some smooth function decaying from the polar angle, from the polar direction to the equator. That is another example I tried to.
You showed the previous plot. Maximum.
Yeah, so a range, here is a more stronger, so stronger selection effect, smaller angle.
And what would be, if you were identifying through the kilonova, what would be a reasonable guesstimate for this electromagnetic, like where in this plot should I look?
Yeah, so that is something that's unclear even from the theoretical work yet. And also it depends on the color you are talking about, because this is not only, you first need to know how the electromagnetic emission look like, and then you need to ask, how likely will your telescope be able to observe that in certain band or so. So for example, I try something like you assume 100% detectability if you are face on, but then when you are edge on, you can assume it is only 50%, something like that. So even in that case, which is not shown here, I still see like 2% systematic from that assumption.
Seems to also always go in the positive direction of the thing to get a
yes.
easy work out of it.
Right, because when you are in this case, when you are in this case, you don't know. You mean when you say you don't know, you mean you assume you can observe it from all directions. So there is only one possibility, one direction you can possibly push it to. Okay, so yeah, actually, this is my the first part of the talk about cosmology. Any other questions I can address for the standard siren cosmology part? Okay, if not, let's move on to another topic. So this is another interesting questions we can try to address from the gravitational observation, which is about neutron star nuclear physics. So one interesting distinct feature for gravitational signal coming from binary black holes merger comparing to neutron star merger is that possibly in these neutron star merger signal, they can have tide. When the neutron star, they get close to each other, they can be tidally deformed by each other. And that will distort the gravitational waveform. So it's gonna distort the signal we receive. And how much these neutron stars they are deformed would depend on the properties of the extreme matters inside the neutron star, which is the equation state of the neutron star, basically. And that is a big question in nuclear physics still, because we don't, either theoretically or tabletop experiment on Earth, we cannot really address or we cannot really study the properties of the extreme matter in this very high density, the low temperature status. And neutron star turns out to be an ideal lab for us to study these properties. So if we can capture this tidal effect in the gravitational observation, then we can put some constraint on the equation state of the neutron stars. And that we already have some preliminary constraint from the observation of GW 170817. But generally, these observation of tidal effect, they can tell us the nature of the property of the matters inside the stars. So it allows us to ask questions like this. Are we sure both of the stars inside the binary, they are both neutron stars? Or could they be one neutron star and a black hole? Because even in this type of neutron star black hole system, since there's a neutron star, that neutron star can be tidally deformed and then disrupted by the companion black hole. So you also expect tidal effect in the signal. Sorry, yeah, in the signal. And can we tell apart like these two types of signal, either spun neutron star or a neutron star black hole merger? Well, if you only have one neutron star inside the binary, then you actually would expect the overall tidal effect to be relatively smaller than the system with two neutron stars. So what we can do is that as we develop our understanding about the neutron star equation state, we observe, say, tides for various events. But let's say in the population of observation, you notice that one of them tends to be relatively quiet in tide. Then one possible explanation for this is that it might be an outlier. It might be a neutron star black hole living in the population. Okay, so that is one questions we can ask. Another question we can ask from this kind of tidal observation is the existence of exotic matter cores. So at the center of this neutron star, that is a very high density region, and there are theoretical predictions saying that possibly some of the matter, they can go through phase transition and maybe they become quark matter or something else. So possibly at the center of the neutron star, they can host some exotic matter cores. And the more massive these neutron stars are, the larger the core you would expect. When this kind of core exists, you would expect a smaller tidal effect as well. So what we can do is that we can try to correlate the tidal observation with the mass of neutron stars. Let's say you notice that beyond certain critical mass, the tidal effects start to decay. Then one possible implication for this is the existence of the exotic matter core. And for both type of scenario, we found out that we will be able to either identify or exclude some of them with order 10 to 100 future detections, which can happen in a few years. But of course, after the identification, the next step, you still need numerical simulation, some targeted numerical simulation to really figure out the physical properties of the nature of the stars in the system.
Can you say a bit more, like how low do you go on tidal deformability in that study?
Let me see. I don't think we really assume. So first of all, we did not start with tidal deformability. We actually start with the radius, which is we can convert it. And but the radius for we consider actually a range, like starting from 12, but all the way down to the minimum you can have before it collapses into a black hole, so like 4 or 5 kilometers. You can assume. But of course, how many number of seconds you require will depends on how low you go. The lower you go, then you can feel it.
I was basically wondering how that correlates with this recent nicer measurement that they had of the radius. That seemed to make it very problematic to get like neutron star radii less than 10 kilometers or so.
If they are still neutron star.
I'm basically wondering like if your result requires that you have like a super strong phase transition with very, very small stars, or if it's just already something intermediate.
I don't know if I have a plot for that, but certainly there is a transition, which I don't have the number.
Okay.
But
we can talk later.
Yes, we can just look back to the paper that I don't remember. Okay.
Can I also ask you about the neutron star black hole work that you mentioned? What sorts of mass ratios were you considering in that work? Because that's also going to strongly influence the.
For this one. Yeah, sorry, I just trying to remember. Yes, so for this one, we actually consider very comparable mass, which possibly they don't even exist, but there are some exotic scenarios, say dark matter also. You might have actually comparable mass of black holes, but yeah, so those are mainly for very low mass black holes.
But also very massive neutron stars, which are going to have a really small tidal deformability.
Yeah, so that will affect too.
Which makes it harder to measure, but you're saying so even with very massive neutron stars, that's still an order of 10 to 100 could.
Yeah, so actually the mass of neutron star, comparing to the signal to noise ratio is still the dominant factor whether you can identify the deformability or not. And mass does affect, but slightly less than the fact of signal to noise ratio. Yeah. Okay, so there is yet another questions we can try to answer in neutron star nuclear physics from the gravitational-wave observation, which is about the origin of heavy elements. So half of the heavy elements inside the universe, they were thought to be formed by a rapid neutron capture nucleosynthesis. However, we do not know where did this rapid neutron capture nucleosynthesis, the so-called R process nucleosynthesis. We don't know where they happen in the universe. And it turns out neutron star mergers, either type of them, they can be, they are strong candidates for the production of these heavy elements where the R process can happen. When this type of merger happen, they throw out a lot of neutron-rich material. That is where the R process, nucleosynthesis can happen. And they form a lot of R process element actually. This element, they can later decay, release energy, and that energy can power up electromagnetic emission. That's what that's the kilonova emission we just talked about. So I've been wondering from the LIGO Virgo observations so far, what can we learn, what can we say about the production of heavy elements from the binary mergers? And to look into this, you first need to know what are the ideal conditions that drive the production of heavy elements from binary mergers. And then the second, do LIGO Virgo binary really satisfy those conditions? So that's what I'm going to walk you through now. First, let's focus on binary neutron star merger. When neutron star and neutron star they merge, they can firstly form a hypermassive neutron star, stay in that status for a while before they collapse into a black hole, or it can directly collapse into a black hole. A numerical simulation suggests that these hypermassive neutrons, the longer you can, the longer the system can stay in a hypermassive neutron star, hypermassive neutron star, then they can emit more material, and a lot of this material can then be converted into heavy elements. So how do we get a long-lived hypermassive neutron star? Well, one possibility is you start with less massive neutron star. When your neutron star were lighter, then you also expect lighter hypermassive neutron star. That's easier for the star to resist against gravitational collapse into a black hole. So possibly they can have a longer lifetime. But do we have these light neutron stars in LIGO Virgo's binary? Here is a distribution of the neutron star mass in our galaxy. So we already have a lot of observation. We do have good statistics. Here is a distribution of that. But for the neutron star inside either the binary neutron star or neutron star black hole merger we observed so far, what you see here, these lines are the median of the neutron star mass we inferred from our detections. And as you can see, it seems that LIGO Virgo neutron star tend to be heavier than what we have in our galaxy. But this trend, we still need more observation to really confirm that this trend is still low statistic right now. Go ahead.
Is your inference of more gold, less gold, just entirely based on how much mass you can potentially eject, or on the composition?
You're fixing everything else, yes.
Okay, so just on the amount of mass, because then even if you have like more massive neutron stars, it will depend largely on the mass ratio, because if you can tightly disrupt the lighter neutron star, you can get a very massive disk. And if you unbind 50% of that might.
It's a simplified scenario, just trying to say that lighter neutron star are possibly easier for long-lived hypermassive neutron star. Okay, so that is one thing. Neutron star mass is one factor. Another property that can affect how much material being thrown out, or how long is the lifetime of the merger remnant, is the equation of state. So if the materials inside a neutron star, they are stiffer, then that they can resist the star from collapsing better. However, we don't know what is the equation of state of neutron star, as we mentioned. We do have some constraint from gravitational wave. We also have independent constraint from radio and X-ray observations. And here are several equation of state that are still consistent with all of these observations. And as you can see, there are still a wide range of them. So this equation of state, all of them, they give us some projection. They give us a prediction of what is the mass and the radius relations for the neutron star. For a given neutron star mass, if the equation of state are able to support a larger radius, so going to the right-hand side of the plot, that is a stiffer equation of state. And you would expect more heavy elements being produced if that is a true neutron star equation of state. But definitely we need to better converge on the equation of state to really settle this down. Now let's move on to neutron star black holes merger. When neutron star merge with the black hole, if the tidal radius of the neutron star is larger than the isco radius of the innermost stable circular orbit of the black hole, then the neutron star can be tidally disrupted by the black hole and throw out material. But if it is the other way around, then the neutron star can be directly swallowed by the black hole. So that is the mass ratio we just talked about. Yeah. So if you want the production of heavy elements, then you do want the isco radius of the black hole to be as small as possible. And one way to make a smaller isco radius is to start with smaller black hole. So we do have some idea of the black hole mass distribution from LIGO Virgo's observations. But this one is actually for binary black holes mergers observation, because we have a lot of them. Already, even for them, we have two distinct distributions here. Here's the black hole mass distribution. And the reason that we have two very different distributions because of one special event, that one. And in that one, there is one of the star inside has 2.6 solar mass, but we are not sure about the nature of that particular star. Depending on whether you assume it is a neutron star or a black hole, it ends up in two cases. So that's why they have two very different distribution of black hole mass. But for the black hole inside a neutron star black hole, we have even lower statistics. We only have two events. So these are the two. So far, we don't have good idea. Only thing we can say is possibly we don't have that many low mass black holes inside the neutron star black holes merger. But definitely we need more observation as well. Okay, another property that affects your ISCO radius is the spin of the black hole. If the spinning axis of the black hole align with the total angular momentum of the system, so the blue and the yellow arrow there, then the ISCO radius would also be smaller. However, if you look at the neutron star black holes merger we observed so far, that the cartoon there already shows you, we don't have that much support along the spin aligned direction. So again, that is not very ideal for the production of heavy elements. Okay, so now we go through several properties that affect the amount of heavy elements produced from individual event. But if you want to figure out what is the total contribution of heavy elements, total contribution from binary merger to the heavy elements production, then one more missing piece of information is how often do these binary merge in the past, astrophysical rate of binary mergers. What you see here is the astrophysical rate for both the binary neutron star merger and the neutron star black holes merger we infer from LIGO and Virgo observation. There are wide uncertainty here, but roughly we can possibly say that binary neutron stars tend to merge more often than neutron star black holes. All right, so now we can combine all these information from observation, plug them into the result of numerical simulations, then we can quantify the total amount of heavy elements being produced from both types of systems. And we have mentioned a lot of source of uncertainty here from observation. There are also uncertainty from numerical simulation as well. But we found out that even so, even if we consider all these uncertainty, still we can say that like binary neutron star merger likely produce more heavy elements, like altogether, I mean, all the binary neutron star merger altogether, they can produce more heavy elements than neutron star black holes mergers in the past 2.5 billion years. And I recently found these questions around the heavy elements production from binary merger very exciting because when we are conducting this estimate, we noticed that it is the mass, the spin, and the astrophysical rate of binary mergers that dominate the uncertainty of these calculations. And as a LIGO members, we know that these three properties are gonna converge rapidly. Like with only next 2-3 years of observation, these properties will converge to the level that is good enough for us to say something interesting about the heavy element productions from binary mergers. And some of you might notice that somehow I constrain my statement within the recent history, recent 2.5 billion years. And the reason for that is because, of course, our detections are relatively local now. But when we start to have this observation at higher redshift, then that means we can not only talk about recent heavy elements production history, but we actually can reconstruct the entire heavy element production history over the cosmic times at different stages. So I find that very exciting. All right. So
sorry, I'm
yes.
having a naive confusion. Like, so what is the time estimate you have associated with the binary neutron star? Like, you said like 2.5 billion years corresponding to the neutron star black hole, but then like a few binary neutron star mergers can give you the same amount, or?
Which amount do you mean?
Are you talking about like a single event would produce like more?
Oh, no, so that is altogether. So you have to multiply it by the astrophysical rate as well.
So this is like binary neutron stars in our galaxy?
No, binary neutron star mergers out to, well, actually it's a time, it's a concept of time. So within 2.5 billion years, then all the binary neutron star merger happen in past 2.5 billion years, their production of heavy elements will be more than all the neutron star black holes merged.
I'm sorry.
Okay, so just to summarize, we know that it's a very exciting time for the gravitational wave field. We conclude our third observing round. We have order 10 binary black holes merger detection, a few neutron star black hole and binary neutron star merger detections a year. But this number is going to grow by 1 to 2 orders of magnitudes only in the next few years. So there are a lot of possibilities we can try to answer various questions. We also have the next generation detectors being planned. And that basically at that sensitivity, we're talking about detection of all the stellar mass binary all the stellar mass binary mergers in the universe. We'll be able to detect them, and that's actually different windows for us. We have been looking into what kind of cosmology we can do, and recently I put out a paper about discussing what can we learn about the galaxy formation black hole seeding problem as well. So a lot of work to be done, and a lot of work can be done here. And I will stop here. Thank you for your attention.
Hsin-Yu? Yes, Caroline, please go ahead.
Can I ask a follow-up question about your discussion of the rates for these heavy element production? How do the uncertainties in the R process, nucleosynthesis rates and so on compare to the uncertainties that you get just from like how much matter you're injecting and influencing the rates you get at the end of the day?
You mean the individual species?
What's that?
You mean the individual species of our process elements, or?
Yeah, when you're quoting like specific results about gold, say, I mean, how much do the uncertainties in the nucleotides of the R process
I see. So
compared to the uncertainties you discussed today?
Yeah, so I think I haven't seen a comparison between the total amount and the individual element. Like either either people try to simulate the patterns, or other group of people, they only focus on the total mass produced from the system. So what we did was only based on the total mass simulation, which didn't go into the details of individual species, which is something
I see.
Yeah, something we will want to look into, especially when we have the resolved spectra from the kilonova emission. Yes.
Maybe along those lines, how reliable do you think are those two black hole neutron star events? Because they would seem to suggest there's no matter left behind. The uncertainty is basically, yeah, I mean, what do you expect for the population just based on those two events? You know, what the feeling there is? Because I mean, you bias it to a very negative side. You said, well, they have so little spin, so there can be no mass, and then you have zero mass ejection from neutron star black hole effectively if they look like those events, right? And then they would not give you anything, irrespective of individual rates. So I guess I'm wondering,
even if you do, like possibly we do have lighter black holes like below the mass gap, but we probably don't have that many of them. With two, I cannot bet.
No, but I mean, even like a 5 solar mass black hole with extremal spin, I think would be tricky, right?
That would be tricky. But that's rare too.
Yeah, exactly. But okay.
Yeah, and also the spin, none of them are like on the positive side. So.
More questions?
For the Hubble constant, like there was this bias that you showed in the plot. So like what would be the major limitations right now? Are there more theoretical systematics or observational systematics that give rise to this?
I'm gonna say both. Like we don't know. There are so many possible models with different geometry for the kilonova simulations, and they all look different. Observationally, you will need a good number of kilonova observation, and then you need to compare it to what you observe from the gravitational wave side, which also itself has its uncertainty to really get some idea. So I am a bit pessimistic if we only have, for example, EM and the gravitational wave observations, so both of them are only coming from observation. see if I have a plot. Maybe not. But basically, I try to do something like I ask, okay, if you learn something from electromagnetic wave side, you have some unbiased estimate, let's say. But gravitational wave side, you also have some estimate of binary inclination angle. So in principle, if there is some bias in between after a certain number of population, you should be able to reveal this bias. However, that is difficult because at least we know from the gravitational wave side for sure, we are not able to resolve the inclination angle with good uncertainty at all. So that will require a big population of them to reveal or resolve this bias.
I guess I was wondering, when you did this estimate, you assumed that, say, you observe 100% from face on and 50%. But I assume this will be also very much distance dependent, because let's say it's less bright by some number of percent, but by the time you are close enough, you probably have volume limit. You've seen them all in any case. So meaning that if you improve the sensitivity of the search or something like that, you should have this gets reached, you get rid of this. So what is there a way around by just focusing on close routing by or deeper searches? I don't know.
Yeah, that is also possible. So yeah, for that calculation I was just simplifying the situation and just try to get a sense of how much bias we would get from that. But certainly, yeah, there should be a distance dependency or the telescope dependency, basically, color dependency, like all that should be taken into account in realistic case. So yeah, possibly we can try to focus on nearby population, and maybe they will be easier for us to reveal the bias but again, nearby you don't expect that many, so that might take time. Good too. Yeah, to figure out how many we need, you will really need to like choose one telescope, let's say LST, and then let's see how many do you need. And also you need some numerical simulation that is also uncertain. Like we just don't know, and we don't have a good way to estimate how many of them we need.
More questions? Nadia?
Your plot is very cute, but it violates the no hair theorem.
No, I know. Yeah, the star doesn't look that shape either.
Exotic star is modified gravity. Okay.
Questions? Do we have any questions from Zoom? But yeah, there is no one on Zoom, so Chanshu, please go ahead.
So about the different heavy element production from binary neutron stars. So can that be tested from, like, for example, observation? For example, would that produce different light curves, something like that?
Different light curve. Different chemical component. That's something that you can possibly capture from spectroscopy. Different light curve. I guess it's just a simple scaling that is, if it's brighter, then possibly that's more materials being produced. That's something that's more straightforward. Yeah, and yeah, I guess it's trivial that we know that possibly we'll first try to constrain and get a better idea of how much total amount of heavy elements being produced, and then we will be able to probably take a longer time for us to look into the individual spectra.
More questions?
Maybe just quickly, I'm just trying to understand the sources of theoretical uncertainties in simulations. Is it an uncertainty in the equation of state, and as a result, you have different kilonova spectrum, or what is the main source of uncertainty there?
Like the one Caroline mentioned, like, for example, this what exactly happening in this area? Like what are the patterns of our process elements you're gonna produce from these region? That is unclear, and that is a complicated
But
problem.
does that trace back ultimately to uncertainties in the equation of state and like?
Yeah, you need to start with certain equation of state,
Yes.
and then you can get different patterns and
The problem is the lifetime of the random, because the kilo
Lifetime of the random.
component, one sourced by the disk, this is where your gold comes from. You'd always have that, and you have another one sourced by basically by the surface of the star. They differ, like the stuff that comes out in the polar direction has more protons, and that suppresses formation of heavy elements. So if you basically have too much of this one component, like you could distinguish between the two cases.
I see.
And if you have
For neutron star black hole, you would not have that.
I see.
Right? So for neutron star black hole, you just have this disk image.
So the lifetime of that star is most sensitive, from my understanding, the mass of the binary, because depending on the mass.
And your equation of state, right?
Right. Okay. I see. And obviously the equation of state. Okay.
And also, if you have the random, that's a fast for longer. It's going to be
And also the magnetic field and angular momentum constant. But then this picture gets super.
I see.
By the time we hear words magnetic field, we know that this is.
So we stop the discussion.
Yes,